Hello everyone, today I'm going to speak with you about aromaticity and kind of further develop molecular orbital theory, at least your understanding up to this point. So if you recall orbital mixing, so going from say an S subshell or S orbital, which is atomic, right, and hybridizing to something that's lower in energy to a sigma orbital. Okay, so in other words, this is going to be your hybridization. Same goes for p orbitals, right? So that's the next energy level up. I know I'm not going upwards in terms of energy here, but at least what I'm trying to depict. But hybridization leads from p orbitals to pi bonds, right, or pi orbitals, molecular orbitals. So today we're going to be chiefly concerned with our pi molecular orbitals because those are going to be the electrons that are going to be moving about and contributing to a particular structure's rigidity and how that is actually stabilized via resonance. Okay. So the first thing we're going to go over is linear compounds. So we'll start off with an ion. So in this case, it's going to be a cation. So there's a line structure for an allylic cation. So it's a vinyl group with a carbocation linking off of it. Right, so it's going to be sp2 hybridized. So it'll be sp2 hybridized construct throughout. Now, that means that there's going to be a total of 3 carbon nuclei, as you see here, and there's just going to be 2 pi electrons basically flip-flopping back and forth between these two. So you can imagine resonance structures here. So there's some kind of resonance hybrid between the two. Okay. So molecular orbital theory, at least with respect to more than 2 nuclei, so this is now 3 nuclei. This is kind of baby steps that I'm going to be introducing to you. So remember that you're starting off with some kind of p orbital, right? So each one of these carbons has a p orbital that can, kind of react with, or not react, but interact rather with neighboring carbons, right? And there's always that sigma bond that's been established in keeping everything together, okay? So you'll see that, based on energetics from lower to higher, you'll see overlap on the lower end, and then in higher energy, you're going to see that things kind of split apart or create what are referred to as nodal planes, which are perpendicular to the actual bond itself, okay? So if we were to do if I were to do an illustration for you of an energy diagram here, increasing energy. Okay. Now somewhere in the middle here is where the p orbitals would lie, right? So, and then right there, centered in the middle of each one of those lobes, is going to be the actual nucleus itself, the carbon nucleus. Okay, so at lower energy, everything is going to be in agreement. So like how I described in chapter 3, these are not actual charges, they're phases. Remember, you can kind of think of a dolphin going in and out of the surface of the water, right? So submerged, it's going to be in the negative, say, or positive, I guess the way they look at it. And then, above and over is going to be negative, right? So up and down about a particular, a 0 point, right? So in other words, there's going to be a particular wavelength or what have you in which those electrons will go and kind of be about this particular construct. So with wave theory, so we have 1, 2, 3 all in agreement, and if we have non-bonding, so this is going to be bonding. Okay. So it means all of these particular p orbitals that have been hybridized to being pi bonds are basically in harmony, right? But if we consider what's on page 690, at the top of page 690, you're going to see sort of a void, if you will. Sorry, not 690, wrong page. 688 rather. So you're going to have those 3 nuclei again. And the book uses shading. I use plus and minus because I have to be relegated to just using black and white, right? So, so if this is non-binding, essentially this is going to be the same energy level as just the p-orbitals by themselves about that particular nucleus non-bonded, okay? Now, if you actually have nodal platons like what I referred to earlier, so this is going to be non-bonding, again, because there's a complete void between one nuclei to the next there, okay? So in other words, there's no overlap. Okay, so we take the highest energy molecular orbital, that is going to be completely in disagreement in terms of phase, right? So this will be introducing what is referred to as nodal planes. Okay, this is what is referred to as destructive interference. Okay, so remember that there are going to be 2 electrons that fill a particular orbital. In this case, this is going to be pi 1. And then you're going to have pi 2 pi star up here. Okay. Now, notice how between the difference between non-bonding and anti-bonding. The anti-bonding is again when there's a complete disagreement in terms of phases, where this is just a complete lapse and void per a whole nucleus. Okay. Now, what does that actually mean for valence bond theory? Well, it's a little bit different. And the valence bond theory is just going to show you sort of a static representation of, let's say, what type of line structure like I've drawn here before, right? You'll see these sort of lobes in each one. And that's a good way to actually show what you see in terms of agreement in phases, like how you see how I've depicted right here. But molecular orbital theory or molecular diagrams where you see those overlaps, you're going to see sort of a better depiction of those particular orbitals. Okay. So let's take a look now at butadiene, 1,3-butadiene. Okay, so now that's going to be 4 total nuclei. Okay, again, it's going to be linear. Okay, if you wanted to take a look at that in your text, that particular figure I'm referring to, you would look at page 692. Okay, so instead of 2 pi electrons, we're now looking at a 4. Okay, so 1,3-butadiene is going to look like that as a line structure. Notice that there's no charge, but still there's an sp2 construct throughout the whole linear chain. Okay, so again, 1, 2, 3, 4 pi bonds in total, or sorry, pi electrons rather in total. Okay, so if we have, again, doing this energy diagram, okay, so there's the p orbitals there, non-interacting, right? P atomic orbitals, rather. So AOs. And then you have 2 sets of bonding. So this is sort of an energetic barrier between bonding and anti-bonding. Again, all in agreement here. And then if you introduce the first nodal plane, or i.e. that first sort of flip in phase. No, I'm not drawing these proportional. But again, if you're looking for perfection, you can see that depicted in your text. Okay. So this is going to be 1 nodal plane. Is that going to disrupt the bond between 2 nuclei? No, it is not. Okay, so that's the distinction between what you see above and below. Okay, so you see everything kind of working harmoniously, and all 4 electrons are moving about in a concerted fashion, all in agreement about the same phase. There's going to be a split or a void for that next energy level up, right? Because in increasing energy, you're going to see that kind of split, if you will, right? So in other words, you can see these as being, let's say, negative, and these 2 as being positive. Okay. But as you get into higher orbitals, energy orbitals rather, it's going to be pi 1, or sorry, pi 2, pi 1 down below. Okay. So you're going to have not 1, but now 2 pi orbital, or sorry, nodal planes. So what that's going to do is you're going to introduce now 2, because you want to have symmetry, right? We have an even number of nuclei here. So in order to have 2 nodal planes, you can't have it kind of offset. So 1 here and 1 here, you're going to have it symmetric. Okay, so in this case, this is going to be basically an agreement in the middle. But things are going to be opposite in phase on the wing, right? So in other words, here and here. So that nodal plane is going to exist right here in between these 2 bonds, and everything's going to be in agreement in the center here. Okay. So that means there is going to be overlap in the middle, but there's going to be no overlap in between where these 2 pi bonds are represented. Okay. Now, this is going to be pi 3 star. And then next up is when you have nodal planes about all four, or sorry, between all three bonds. Okay, so it's going to be the highest energy molecular orbital. And again, that's going to be pi star 4. Okay, this is a 3. Sorry, couldn't read that. Okay, so plus, minus, plus, minus, minus, plus, minus, plus. Okay, so in its highest energy, that means that all 4 electrons are out of phase with one another and not overlapping at all. So pretty much each pi electron is about each particular nucleus not overlapping. Okay. Now, what does this actually mean for resonance and something that would be, let's say, in a more cyclic pattern, like let's say benzene or something? Well, remember that there can only be 2 electrons that can occupy a particular orbital, right? So if we were to take butadiene, and again, that's going to be 4 total electrons, right? One's going to have to be going in the direction of the magnetic field, one's going to be opposing. Okay, so there can only be 2 in a particular subshell. In this case, pi 1, pi 2, right? So pi 2 is where you're going to see the highest occupancy molecular orbital. Okay, so or highest occupied molecular orbital. The lowest unoccupied molecular orbital is going to be pi 3. So that means in order for particular orbital to get to this particular energy state, one of these electrons has to go up. Okay. So in other words, it has to jump up in energy one stage, if you will. Okay. So it has to go first up here before it can get promoted up to pi star 4. Okay. All right. So that can be either propagated through light or by some kind of thermal means. Right? So some kind of energetic stimulus would cause that to happen. Okay, so now we're going to look again in an odd count, sort of like the allyl cation here, but now it's going to be an odd count of 7 carbon nuclei that are going to be connected through sigma bonds and have 1, 2, 3, 4, 5, 6 pi bonds that are going to flip around. Okay. Now, this is example or problem 14.26 in your text. So it says the following are 3 pi molecular orbitals for the heptatriene cation. For each molecular orbital, A, determine the number of nodal planes perpendicular to the bonding axes and rank them in order of increasing energy. Okay, so that is going to be not as well depicted, or I probably can't depict it very well, but I'll try. I'll try to do my best here. So let's say there's going to be one going out, other going in, one going out, other going in, one going out, other going in, one going out in terms of nuclei. And then I'm going to have the actual overlap here. Okay. So notice how what I'm drawing here, whoops. Again, there'll be a better depiction of this in your text. Take a look at page 718. Okay, so there's going to be no overlap about the second nucleus or second carbon. Okay. But then there's positive, negative here. Positive on the top, negative on the bottom here. And then negative on the top, positive on the bottom here. Okay, so there's disagreement among four, or actually three nodal planes, if you will. Okay. So what that means is you have a void about these three nuclei, right? So there's no actual electronic overlap, okay? So this is going to be higher energy. Okay, and then if we take another orbital here, so this is A, or depiction A, this is going to be B. Maybe I didn't give myself enough space. Okay, so there's going to be agreement and overlap is going to be much larger here. Okay. All right, so now there are going to be a total of two nodal planes. Okay. And so of all the three that you see here between A, B, and C, this is going to have the lowest energy. Why? Because it has the fewest nodal planes, and I'll show you for C why that's the case. Okay, so for C, again, in, out, in, out, in, out, in. Okay, so we have positive on the top, negative on the bottom. Then we have some overlap here. Again, this is going to be out of phase with what's on the left. So now in total there are going to be 4 nodal planes. So where you see here where there's 2 nuclei in agreement here and 2 nuclei in agreement here, that would mean that between this bond and say this bond, you would have that constructive overlap. Okay. So this is going to be actually highest in energy. Okay, so this would be middle, and this would be lowest energy. Okay, so part B says draw the p atomic orbital contributions on each carbon atom that would give rise to the molecular orbital. So in other words, if I were to draw this in zigzag pattern, it would just go. Let's take this off here, the charge. Okay, so it would go positive, negative, negative, positive, positive, negative, negative, positive, So there's going to be non-bonding between those three spots, or among those three nuclei. Okay. So for the second, that's actually going to be 2 in agreement. So they're p orbitals, in other words. And these three are going to be in agreement. Right, because you see that overlap among the three nuclei, right? And then, again, flipping the phase over once more, and these two having overlapped. Did opposite phase here, sorry about that. Just to see that it reflects what's on the bottom there. Okay. So again, this is more of a p atomic orbital representation of what's in agreement and where those, again, that's not going to change the actual location of the nodal planes. So in other words, if there are two nodal planes about a particular 7 count linear chain, it's going to go 2 in agreement, 3 in agreement, 2 in agreement to be symmetrical on both sides. Okay? So we want things to average out evenly and nicely. Okay, and then so it's going to be the lowest. Again, it's going to be B, C. That is just going to be, I'm going to draw that down here. Hopefully not. This is going to be in the way. Okay, I'll draw it right here. How's that? All right, so that's, again, the p atomic orbital contribution. So there's going to be, again, nodal plane here, nodal plane here, nodal plane here, nodal plane here. So it means you have 2 little sections of overlap, again, about this bond and this bond. And then you're going to have 1, 2, 3, 4 nodes, nodal planes that are going to be, again, symmetrical about the molecule. Okay. For C, identify each inner nuclear region as having either a bonding or antibonding type of contribution. Just told you. Okay, so this is going to be anti-bonding right here. This is also going to be anti-bonding. This is going to be non-bonding. Okay. All right, so, and then it says D, based on your answer to part C, determine whether each, okay, just that for you. All right, so that pretty much wraps up 14.26. Again, this is a 1,3,5 heptatriene cation. So everything's sp2 throughout. Okay, next conceptual question here is how many pi nodal planes, or sorry, how many nodal planes about hexa 135 triene at pi star 6? Okay, so remember that's going to be 6 energy levels, right? In which you're going to have a total 1, 2, 3, 4, 5, 6 electrons, right? So that should be like so. Okay, and then this is kind of the divide between bonding and anti-bonding. So if one electron was basically dispersed about each one of these orbitals, or going all the way up to pi star 6, right up at the top, then that means that you would have, if I were to do the p orbital representation or contribution, it would look something like this. So remember, these 6 nuclei are all connected together via sigma bonds, but there would be a disagreement between each nucleus. Okay, so remember, at each step you're going to introduce more and more nodal planes. So it'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Again, everything's symmetrical from left to right, and you're going to have destructive interference between each particular nucleus. In other words, a perpendicular nodal plane between each one. Okay. All right. On to some easier, sort of less conceptually demanding material here. Identifying pi systems. So, each double bond that I've considered here is going to be 2 pi electrons. Notice how it's a conjugated system, so there's no disruption in an sp2 environment, and those electrons are, have the ability to overlap, right? But if you have a disturbance in that, or you have, let's say, an sp3 carbon wedged in between there, that's sort of a roadblock, if you will, in order to deter any type of overlap. Okay, we're going to take the first example, which is called squalene, which goes into certain types of cosmetic formulations, actually taken from sharks, although I would imagine it's produced synthetically. Okay, so I'm running out of room here, but I'll just do the rotation down. 1, 2, okay. You'll have this in your notes. Okay, this is going to be a symmetric molecule. Exactly knocking it out of the park today. Not that I don't have things to distract me like lawnmowers or anything, but yeah, welcome to the birds. Okay, so we have a complete disturbance, operative word. We have a pi system here. We have a couple sp3 carbons right adjacent to the, or right next to them. In between a next pi system. So there's going to be one pi system here, one pi system here, one pi system here, one here, one here, one here. In your notes, I have this in a linear construct, so it doesn't look so ugly and stupid. So, in other words, the same concept applies. There's just been some rotation here. 1, 2, 3, 4, 5, 6 different pi systems in total. Okay, so let's look at this aromatic structure or derivative, since we'll be leading into aromaticity. Okay, so we have all these electrons, which are actually all part of the same construct, and they're also conjugated to this transalkene. Okay? Are they also conjugated to this? Yes. Are they also conjugated to this? Yes. Okay, so this is an additional pi bond that's actually going to be perpendicular to what's just on the other side of that particular carbon. So that's not going to be part of that plane, right? Because this has to be perpendicular. So this little symbol that I show you right here, it's like a double-ended L or something like that. That is perpendicular to, okay? So these two pi bonds are perpendicular to one another. This particular carbon is going to be sp as opposed to sp2. Okay, so now I'm going to circle the different pi systems, okay? So this is going to be a pi system count. This isn't pi electron count, it's a pi system count. Okay, so this is also going to be sp, these two carbons here. So one of those pi bonds is going to rest perpendicular, and this, all of this is its own separate pi system. Again, because it's going to be conjugated, it's going to be double bond, single bond, 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 double bond, single bond. All right, you get the drift. Okay, so remember also that per the phenyl ring, there's going to be this constant current of electrons going in a cyclic form. Okay, so pi electrons, that is. All right. So kind of an easy exercise there. So let's plunge into aromaticity. So I referred to a phenyl ring just a minute ago. I'll show you benzene. And benzene is a pretty stable aromatic system. And I'm going to describe to you what an aromatic system really consists of. Okay, so benzene is going to be a stable structure stabilized by resonance. So when I say resonance, that means these pi bonds can kind of cascade over. Right? So these two particular forms that you see aren't really going to make a difference in terms of what they are constitutionally. Okay, so this isn't going to be an equilibrium or anything. It's just a resonance form of one another. Okay, so sometimes you'll see. I'm not going to do this, but sometimes you'll see this sort of shorthanded as such. Okay, so just a circle in the middle, just to indicate that those electrons are constantly in flux, right, or constantly in motion, and they are. Okay, but in terms of you know, mechanisms and things like that, I try to stick to you know, the 3 pi bonds that are there. Okay, so up to 3 nodal planes exist. So spatially, I want you to think about that for a minute, because if you have, I'm going to draw a hexagon here. Okay, and I'm going to do my p orbital contribution. Okay. Remember that this ring is going to be a little bit more compact, right? Instead of seeing these, you're thinking a single and double bonds in terms of bond order and length. All this is going to be averaged out to be, you know, X number of picometers. Okay, so let's say if we have pi star 6, just like we saw for hexa 135 tri. Okay, so we still have the same count of pi electrons, right? But those pi electrons need to have a source. Of course, that's going to be the p orbitals. Okay. All right. So now there is going to be a nodal plane that will cross, okay, between this bond and this bond. Same goes diagonally from it, as well as 60 degrees across. So in total, there will be 3 nodal planes, as opposed to what you saw linear for 135 hexatriene, where you could have a total of 5 in pi star 6. Okay. So again, the symmetry about that particular cyclic molecule is where you can see that there's going to be symmetric nodal planes, again, perpendicular to each one of these bonds. Okay. Just across from the ring itself. Okay, so now we're going to get into the Frost diagram method. And if I were to draw and apply Hund's rule, dig through those cobwebs in your head and remember what that must mean. Okay, so we have pi 1, pi 2, pi 3, pi 4 star, pi 5 star, pi 6 star. Okay. And then we're going to have a total of 1, 2, 3, 4, 5, 6 pi electrons. Remember that. Okay. So pi 2 and pi 3 are going to be of equal energy. So that means that 4 of the electrons are going to be slightly higher than the 2 electrons that are going to be in pi 1. Okay, so filling up the pi 1 orbital. But remember that these are constantly going to be in rotation, therefore things are always going to kind of average out to what you see right here. And when you do a Frost diagram, you don't want to have that point, you don't want to have 2 points at the bottom, right? Because if you have that, that's not going to follow Hund's rule. Just an example I'm going to show you here. So I'm going to rotate that hexagon. I'll put pi 1, pi 2, pi 3, pi 4. So again, that's going to be right at the level which you would expect where your p orbitals would be already, right, before they were hybridized. Remember that if they're going to be stable, they're going to have to be lower in energy than what they had energetically from their p origin. Okay. So this isn't going to work for a couple of reasons. One, we have to fill out our orbitals, but per Hund's rule, right, each subshell has to get filled up one electron at a time, right? Because this is going to be lowest energy. I know it's about the same particular energy, right? And just, but we have two singlets here that aren't paired up, right? So lowest energy is when things are paired up and opposite in spin. Okay, so this is going to be an issue. So in other words, this is going to be lower energy overall. And again, you want to have that point at the bottom. So just a note on frost diagrams. So just to list things off for frost diagrams. Again, draw whatever polygon is representative of the Lewis structure. Okay, we'll do another one for cyclopentadienyl cation here in a minute. And 2, place the energy of the non-interacting p orbitals at the center of the polygon. So like I did before, so that's where the dash is. Okay. And then number 3, place the energies of the pi molecular orbitals at the vertices of the polygon. So in other words, where these points are. Okay. Alrighty. So now we're going to get into Huckel's rules and numbers. So an aromatic species is when pi electrons have a 4n plus 2. So n is just going to be any integer, right? So it has to be cyclic. In other words, it can't be a linear chain like you saw in the beginning. It also has to have, it can have an even or odd number of carbons or heteronuclei, as we'll see later. Okay, so heteronuclei, what I mean by that is, either nitrogen or sulfur or oxygen. Nitrogen and oxygen are the most common. Okay, but you have 4n plus 2. So that n integer, that should be 0 or 1 or 2 or et cetera, okay? So in other words, it would be in denominations of like so. It would be 2, 6, 10. 3 times 4 is going to be 12 plus 2, that's going to be 14. Okay, you get the drift. So it's after 2, it's in denominations of 4. Again, 2 just coming from plus 2. Okay, so so in other words, this is going to be where n equals 1, right, for benzene. So in other words, it's going to be aromatic. Now, one thing of note, if you have, let's say, something branching off of any of these carbons in lieu of a hydrogen, for instance, that's not going to change the fact that this is still going to be an aromatic compound. Okay? So, you'll see certain types of species in nature that actually have a benzene derivative, right? Or it's going to be part of the greater sort of compound itself, right? So you can think of still beans and things like that. They have pi systems within them that are aromatic. Okay, so some pheromones might contain something like this as well. Some natural pheromones that are out there. Okay, so there's the aromatic, and then there's the anti-aromatic. Keep frost diagrams around. At least keep that in your mind for a minute. So we're going to look at a particular ion here in a second. Okay, so anti-aromatic. Is when the pi electrons follow the convention of 4n. And that's it. So it's not going to be 4n plus 2. It's just going to be 4n. Okay. So in other words, that would put this particular ion that I just referred to earlier as anti-aromatic. Because you have 1, 2, 3, 4 pi electrons about this particular structure. Remember also, and this is very important, that you need to have an sp2 construct throughout. Remember, you need sort of a place where those electrons can flow, those pi electrons can flow, and have some occupancy, and then some. So things are going to be occupied here, at least how they're drawn out statically, and then this is going to be sort of available as things kind of cascade along. Okay. Now, is this going to be as stable as an aromatic structure? No, it's not. It's actually going to be, and I'm going to show you why with a frost diagram here. Okay, so a frost diagram. Okay, so you have pi 1, pi 2, pi 3, pi 4, pi 5. Okay, so this is right there, or thereabouts, where you would have, your atomic orbital energy, right? Again, energy increasing. Okay, so once again, this is a frost diagram. So if we're going to place those 4 electrons, notice what I'm doing here. So again, I'm following Hund's rule. Okay, so we're going to have those 2 pi electrons that are not coupled, right? So in other words, there's going to be singlet here, and they're not going to be. They're basically about the same energy level that's right there about that p orbital. So in other words, at all times you're going to see these not kind of paired up, and they're going to be in of higher energy. Okay. All right. So 4n. So in other words, it's going to be either a count of 4 or 8. Or 12, or 16, right? Wow, I really botched this. Aromatic, anti-aromatic. Sorry about that. Okay, so with that said, we have. Again, we don't have a full occupancy. So we have partial occupancy about the same energy level, about 2 different or two equal energy, but two different orbitals. Okay. All right, and then there's non-aromatic, and that's when you have an sp3 carbon that's kind of disrupting where those pi electrons can flow. So in other words, the conjugate, not a conjugate acid, what am I looking for? Well, a full octet version, let's put it that way. So this is what is referred to as cyclopentadiene. So this is going to be sp3 right here. And this is going to be sp2. Okay. So in other words, this can't be disrupted. This is going to disrupt any type of flow of electrons. So this is going to be all an sp2 environment. This is going to be an sp3 environment. Okay. Now, let's take the conjugate base of this. Right? So we lose H plus here. Okay, so now we have 1, 2, and then a lone pair. Okay, so now we have these two electrons. Sorry if you can't see that very well. Let me move this over. You have these two low pair electrons that can come in and kick these out here. So now this is going to be resonance stabilized. Okay. And this looks about the same as what you see right here. So these lone pairs are constantly going to be going into the pi system and kicking another one out. So it's constantly going to be in flux, okay? And this kind of anion can actually sandwich up and form some kind of complexes with something like, say, like manganese, like what I did with my grad studies, okay? So this is what is referred to as an aromatic cyclopentadienyl ring, okay? Because you have two lone pair electrons that are actually participating in the pi system. So in other words, this is always going to be in flux, and you're going to have 1, 2, 3, 4, 5, 6 aromatic system, okay? So each one of these carbons is just going to have one hydrogen branching off, right, outside of the ring itself. So this is constantly going to be resonating. Okay. So this is going to have a comparatively lower pKa. I couldn't tell you right off the bat. I think it's somewhere around 16. But nonetheless, this is going to be an aromatic structure. And this is going to be anti-aromatic. Okay, so the next thing I'm going to go over with you is polycyclic structures. So here's a polycyclic aromatic compound, what is referred to as pyrene. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pi electrons. Okay, so 16 pi electrons. Now notice that there's a total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 about the periphery, right? So we have 12 electrons surrounding, but what you want to do is actually take a look at how many pi electrons are about each particular ring, okay? This is all going to be planar. None of it is going to be distorted by any hydrogen sticking up or down here, okay? So everything is going to remain planar, sp2 throughout, right? So you have 3 coordinates here, 3 coordinates here, 3 coordinates everywhere, okay? But this is still considered an aromatic hydrocarbon because you have our aromatic system here, and another aromatic system here, okay? So in other words, this could be equivalent to just having, you know, let's say, or to draw it out lazy, okay? And then there was just this sort of bracket alkene that's just right there that's attaching everything. Okay, so if we were to take the count of all the electrons that are in that particular construct, we would have 14 pi electrons, right? And 14 would follow that 4n plus 2 designation. So, right, you would have n equals 3. So it's 14 pi electrons. Okay? All right, so let's look at an aniline analog. So this is not going to be like naphthalene. Naphthalene has actually a bridge right there in between those two carbons. Okay. So everything's still going to be sp2. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So does that still follow that convention for aromatic? Yes. Okay, but remember, these hydrogens are going to be in there. If things are going to be, you know, sort of in a neat zigzag form, right? So therefore, it's going to kind of change where these hydrogens are going to be placed. And they may actually wedge out as opposed to stick right in there inside of each ring. Okay? Or have a different angle in total. 144 degree angle, so it's going to be a broader than what you typically see for 120 degrees for trigonal planar. Okay. So, but that kind of is an attribute of how strong that kind of overlap is and how structurally robust this particular 10 aniline is. So it's going to be 10 for the count of pi electrons and then aniline. So there's 14 aniline, there's 18 aniline. Okay, so there are different types of aniline compounds, and people are, you know, you'll know what the carbon count is based on the amount of these peripheral pi electron counts and you know what shape or polygon that would be in respect. Okay, so the last thing I'm going to cover with you is heterocyclic compounds, and then we'll do a little quick exercise with aromatic, anti-aromatic, and non-aromatic. should be it for this module, sub-module anyway. Okay, so let's first take the example here in your notes, pyridine. Okay, so this nitrogen is going to be sp2 like everything else. So that means that lone pair has to stick out parallel to the ring, sticking outward, right? So 1, 2, 3 is the pseudo coordinate. Right? So this is going to be 1, 2, 3, 4, 5, 6. That's going to be aromatic. But the thing of note that I want to make here is that this that lone pair does not participate in the pi system. Not like how you saw earlier with that cyclopentadienyl anion, okay? So there's a difference. Also, pyridine itself is weakly basic, so it'll pick up a hydronium ion, or H+, whatever you want to call it. And is that going to disrupt aromaticity? No. It's just going to be positively charged. You probably have some kind of anion there to stabilize the charge. Okay, so that's pyridine. It's an aromatic compound. That's an aromatic cation. Here's furan. Okay, so remember that furan it's a cyclic ether, but one of those lone pairs, not both, just one, can actually go into the pi system. Okay, so we have some resonance stability here. Okay, so we still have a full octet about that oxygen now. We have that pi bond that got kicked out to be a lone pair about that particular carbon. So there's charge separation, right? Okay, so there's a negative charge there on the left. So it's pretty much a dead end in terms of resonance structures. You can't push that over, and then, well, I guess you could, but in general, these things are going to be resonance stabilized just by one lone pair. So in other words, two of those lone pair electrons feeding into the pi system. So this is what is going to be, again, it's going to follow 4n plus 2, so it's also going to be, so n equals 1, aromatic. Okay. Here's another example, pyrrole. You'll see pyrrole a little bit more in the next module, module 3. Remember that nitrogen has a lone pair when it's in the ground state. So this lone pair can actually also contribute to resonance. So, can't really see that. Okay, so that's going to be a positive charge about the nitrogen and then a negative charge right there. Again, same kind of resonance that you can have Okay, so in other words, you can have some kind of charge separation from that lone pair kind of feeding into the pi system. Okay, so remember that these things are going to happen really fast. So there's going to be, for every kind of heteroatom like you see right here, with the exception of pyridine, because that lone pair is going to be parallel. In other words, it's not going to be perpendicular to the construct of the ring, where things can overlap, like you see here with oxygen, like you see here with nitrogen. Think of things being kind of a little bit closer to where all these other pi electrons are, okay? In terms of overlapping about the same plane. Okay, so let's look at problem 14.20. I'll pause here for a minute and then I'll put those examples up. Okay, so problem 14.20, we have example A. So we have 2 pi electrons here within the ring that are clearly established, but then we have one of these lone pairs that can feed in. So in other words, this is going to be anti-aromatic. Okay. Next example is basically a benzene ring fused in with a pyridine ring. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about that ring, or those 2 rings. So that's going to be 10 pi electrons. 10 pi's. No, 10 pi electrons. So that's going to follow 4n plus 2. And this is going to follow 4n. Okay, so this is going to be aromatic. Okay. All right, next one is going to be this guy here. So we have 2 lone pair electrons that can feed in. 2, 4, 6, 8. So it's going to be a 4n convention. So, and n is going to be equal to 2. N is going to be equal to 1 at this top example. So this is also going to be anti-aromatic. Okay. Here's a sulfur-containing compound. So we have a lone pair here. We have, so it's 1, 2, 3, 4, 5, 6. Okay, so we would think that would be follow aromatic. However, this isn't fully conjugated, right? Because you have an sp3 carbon that's disrupting it. So in other words, this is going to be non-aromatic. All right, moving on. So this is a linear one. That should be a dead giveaway that things are not going to be aromatic at all. Okay, so we could think that there are going to be 6 pi electrons, but again, not cyclic. So non-aromatic. Next is this particular compound above. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 just like what we see up here. Remember that for this particular pyridine portion, that lone pair is going to be sticking out. But since this is going to be sp3 hybridized, right, it's going to have that lone pair feed into the system, into the pi system. Okay, so again, 2 electrons from a lone pair can go into the pi system. So this is going to be 10 pi electrons aromatic. Okay. Next one here, we have an sp3 carbon there. Now that may disrupt the overall conjugation. However, we still have an aromatic portion right there on the left. So therefore, there's 6 pi electrons. And again, that is going to be aromatic. So cyclic, 6 pi electrons following the 4n plus 2, n equals 1. Okay. All right, there you have it. Okay, so we'll go over these last couple of examples in your notes, and then we'll wrap things up. Okay, so the first one is a cyclopropene anion. So that's just going to be this particular ion. Okay, so again, you have a lone pair that can feed in, and then you have a double bond here. So that's going to be a total of 4 pi electrons. Okay, so 4n, n is equal to 1, so therefore it's going to be anti-aromatic. Okay. All right, we've already looked at cyclopentadienyl cations and anions. So just to reiterate, you have 4n for this, n equals 1 again. So that's going to be anti-aromatic. And then as shown before, this can resonate with these pi bonds, this lone pair that I'm referring to above, so it's going to be 4n plus 2, n equals 1, aromatic. Last one, conjugate base of pyrrole. So remember that still one of those lone pairs can feed into the pi system. So in other words, this is also going to be 1, 2, 3, 4, 5, 6. So 4n plus 2 again, n equals 1. So aromatic. It would be an aromatic anion. All right, so that wraps things up. For Module 2A. Be sure to check in for office hours if you want to see some extra examples, or you want to kind of clarify anything that I've discussed here today. All right, have a good one. Take it easy.